Okay, so after the first part of this talk on the Carnac Alignments, we're now going to see how the same geometry that was used to position the latitude of Carnac was actually used to situate the pyramids on the Giza plateau. So here they are. This is the satellite view of the Great Pyramid at the top here. Great Pyramid, and then the Kephren Pyramid in the middle. And there's a thing down here, right? You see that line there? There? They call that the Kaphre Causeway. Officially, it's a kind of funereal path where you come up from the lower temple here, which is called the Valley Temple, and then you come up this path to the upper temple, and there you go. Well, there's no connection between this temple and the pyramid. Right. So that's the sort of official explanation. Now, this may look like a sort of secondary kind of thing compared with the pyramids, but in fact, it's an incredible amount of work. Herodotus said that the causeway for the Cheops pyramid, which is underground and was only discovered last year, and hasn't been revealed at all. We just heard that it was discovered, and we've had no information since about exactly what's going on. But Herodotus said that that was more work than the pyramid itself. So if we look at this Kephren Causeway, which is well known, here it is. It actually goes into the Valley Temple, the straight line. It's a perfectly straight line. And it actually goes into the Valley Temple here. There's a sort of angular corridor in the Valley Temple, which leads up to this end wall. And it enters a little bit as well, on a diagonal, into the upper temple here. So if you trace this line on Google Earth, oh, well, first of all, look. Here's an old photograph of it. So you can see it's a very monumental structure. The land is not flat, it goes down and up, and the whole thing has been made perfectly flat and perfectly straight over 500 meters long with massive stones. So it's an enormous work to have made this. This is the bit that goes down into the Valley Temple. It's still in the same straight line. Here's an old sort of engraving which gives the impression of the Valley Temple here. When this was made, there was no knowledge of the temple here, which is called the Sphinx Temple, which was under the sand and has been discovered since. So there's the Valley Temple with this causeway, and you can see it comes up out of the, it's a lot of work went into it. This is another picture of it coming down here into you can see it actually going right into the temple here, the Valley Temple. Now, if we look at the angle on this thing, there it goes into the temple here. That's the Google Earth version of it. And then it goes down into the Valley Temple, okay, like that. You can see here the wall, the inner wall that follows that as the corridor goes down right to the end wall here. So if we look at that angle there, we discover that that line is on an angle of 284.04 degrees. We can calculate it very, very precisely because the corridor here is quite narrow. And of course, you can see it's nearly 500 meters long. So you can get a very precise angle on that. And this is the angle, 284.04 degrees. Now, if you take that away from 270, which is north, 90, 180, 270 is west, you get the angle which is north of west. So 284 minus 0.04 minus 270 gives you 14.04. If you take the tangent of that, the value is 0.25 or 1/4. What does that mean? It's a quadruple square. So we saw that we had a triple square in Carnac, and we see here on the Giza plateau that this causeway traces precisely the diagonal of a quadruple square with respect to the cardinal directions. Okay, so that's very interesting. So these ancient Egyptians actually have traced out this axis on a very large scale, a lot of work to be involved in this. Now let's look at the base dimensions of the Great Pyramid. You may know these already. It's known that it's 440 Royal Egyptian cubits, but how long is the Royal Egyptian cubit? So if we take the different measurements, there's slightly different measurements, as you can see. The longest side is the south side, which is 230.45 meters, 454, and the shortest side is the north side, 230.253, and then the west, 230. But there's very slight differences, like 10 centimeters difference between the different sides. If you take an Egyptian cubit of 0.5236 meters as your length, and you multiply that by 440, which is the number of cubits, you get this value, 230.384, which is the four sides added together divided by 4. In other words, the average length of the side is 230.3645. So we have, in fact, a little less than about 2 centimeters difference, which is accurate to 99.99%. For the use of the Egyptian cubit of 0.5236. So these measurements were made by Flinders Petrie, and they are recognized as being the most precise measurements ever made of the Great Pyramid. Incredible detail he went to get these exact measurements. So we can say quite clearly that the length of this cubit used here is 0.5236 meters. We get confirmation of that inside the King's Chamber, which is 52.36 meters wide. 5.236 meters wide, 10 cubits, and it's 20 cubits long. So it's a double square, 10 cubits by 20 cubits. That's the base plan of the chamber. Now, as 0.5236 is phi squared over 5, phi is the golden ratio, it's the equivalent of 2.618 over 5, or if we multiply 2.618 by 2, it gives us 5.236. So there's a direct relationship between the Royal Egyptian cubit expressed in meters and the golden ratio. This would clearly indicate a link between the length of the Royal Egyptian cubit and the meter, because this is numerical. It's a numerical relationship. Now, if you measure the length of this causeway from the very entrance of the chapel here, of the upper temple, right from the outer wall of the upper temple, right down inside the inner temple to the base here, that measurement is 523.66 meters. That's 1,000 Egyptian cubits. So this is a good example of how the Royal Egyptian cubit was used, because it's 1,000, the exact length of this causeway. Now, what you must realize is that the diagonal of a quadruple square is equal to the square root of 17. It's 1 by 4, 1 by 4, so 4 squared is 16, plus 1, 17. 16 plus 1, 17, so the diagonal of the quadruple square is the square root of 17. So if you take this length of 523.6 meters and you divide it by the square root of 17, this gives you the length of one side here. Okay? Gives you the length of the side because you have 523.6 meters on a value which is root 17. If you want the side value, you divide by root 17, and this gives you a value of 127 meters. This is quite interesting because you get an exact number of meters when you're dividing by a square root, which is rather strange. Square roots are these numbers, irrational numbers that go on forever. So you get this whole number, but what's much more strange is that 127 is a very special number because it's 5,000 inches. 127 meters is exactly 5,000 inches. The centimeter, 1 inch is equal to 2.54 centimeters. 2.54 is twice 127. So the relationship between the inch and the meter, or the centimeter, seems to be expressed in this geometry. Because it's a 1 by 4 ratio, so if you have 5,000 inches on the short side, then you have 20,000 inches along the long side. Now that's quite astounding, that with 1,000 Royal Egyptian cubits along the diagonal, you get 20,000 exactly, not approximately, exactly 20,000 inches, English inches, along the east-west line. So that gives us a definition in inches of the Royal Egyptian cubit, which is 20 multiplied by 17, root 17 over 4. So that's the definition of the relationship between a Royal Egyptian cubit and English inches. And that relationship is expressed in this geometry and these measurements. Okay? So the idea that the English foot, the English inch, the English foot is linked to this, which comes from John Michel's work, is perfectly true. But the actual link with the meter, he didn't connect to because he was convinced that the meter was Napoleon's invention and didn't realize that Napoleon had gone and taken it from Egypt. That's what I reckon. Now, let's go a bit closer into this. So if we take an east-west line and we put a quadruple square along the Kaphre Causeway, the diagonal is east-west by definition, right? Because if we put the quadruple square east-west, the diagonal is the Kaphre Causeway. If we put it along the Kaphre Causeway like this, slope it, then the other diagonal is horizontal. And we saw in the first part on Carnac that the other diagonal gives a solstice angle. So I checked up on the solstice angle at the Giza plateau. Here we have the Great Pyramid, right? The year 3200 BC. Now this is older than the official date given for the Great Pyramid, but it corresponds to the date given by thermoluminescence technique done by Robert Temple and a Greek scientist friend of his. They got an actual physical date for the Great Pyramid at 3200 BC. So I chose that particular date of 3200 BC as the date of the construction of the Great Pyramid. This doesn't fit with the Kephren and Cheops theory, but then the Cheops theory is very tenuous, to say the least. But anyway, by taking this date, we get the angle here of the solstice as 28.072. This comes from a program developed by James Q. Jacobs and Victor Reiss, which called astro-geometry, which enables you to calculate solstice and moon angles at any latitude at any time on Earth. Very precise. They've worked many years on this. And so this is the exact solstice angle, 28.072, for the Great Pyramid in 3200 BC. Now, if we take the other diagonal of a quadruple square, it's double the 14.04 of the first one, gives you 28.07. So we have exactly the same principle as in Carnac, where here in Carnac, it's the triple square, which gives the solstice angle when doubled. In Giza, it's the quadruple square, which gives the solstice angle when doubled. And so you see that it's quite clear that the choice of these two latitudes is linked to exactly the same principle. Now, of course, we saw that the double angle of the triple square gave us a Pythagorean triangle, the 3-4-5 triangle. Oh, this is a picture. I didn't point that out, but if you look carefully, you see that I've positioned this quadruple square right at the entrance of the temple and down the line here, and the diagonal actually goes through the head of the Sphinx. So that if you stand further down this line to watch sunset at summer solstice, that's what you'll see. The sun setting between the two pyramids behind the Sphinx head. That's an image I calculated on the Google Earth thing. Isn't that interesting? But is there special geometry linked to this angle? We saw that in Carnac it was a 3-4-5 triangle. Well, let's come back to this theory I developed, how to get a Pythagorean triangle from any two numbers. Here the numbers are 1 and 4. So if we feed them in, so that's the double angle. If we feed them in, 2 times 1 times 4 is 8. 4 squared minus 1, 15. 4 squared plus 1, 17. This is a Pythagoras triangle, the 8, 15, 17. So the solstice angle at Giza Plateau is also a Pythagoras triangle. In other words, a right-angled triangle with whole numbers on the 3 sides. So that's very particular, and this idea, I think, has never been seen before. So the latitude of the Giza Plateau is chosen for the same reasons as the latitude at Carnac.